A question you might have had in the past is like, why do molecules take on the shapes they do? And you can see from these examples here that there's lots and lots of different orientations, geometries, stuff like that. And they range from things like water and ammonia, which you can see, but there's also some other fun things, cocaine, just say no, kids. Anyway, caffeine, one of my personal favorites, boron trifluoride, and lots of other examples. And all of these molecules take on their shapes for a specific reason. And that's kind of what we're going to be learning in this section. Like, how do you take the atoms and make molecules? And along the way, we're going to use what we looked at the end of Chem 221 when we talked about atomic orbitals. We'll see how the atomic orbitals have an influence on how the molecules come together. It's a pretty cool chapter. So by the end of this section, you'll be able to understand the bonding patterns you're seeing in these molecules, and that's kind of a powerful thing when it comes to chemistry. Some questions, though, definitely we need to consider, like how is a molecule, or polyatomic ion for that matter, held together? Like, what's the glue that makes them stick, that makes the atoms stick together? Why are the atoms at those weird angles? And can you predict what's happening? Like, why aren't they all flat? I mean, we draw them flat, so why aren't they all flat? Can we predict the structure? And of course, the answer to that's going to be yes, because this is chemistry. But anyway, we'll also look a little bit about how the structure we observe is related to chemical and physical properties. So like why some things boil higher and lower, for example. This is a conversation we'll be looking at this entire quarter. As a quick review from Chem 221, there's basically two extreme forms of chemical bonding, all right? One form that we talked about a lot in Chem 221 was ionic bonds. And in an ionic bond, the metal usually is losing an electron to the nonmetal, and the resulting positive-negative charge is called an ionic bond. And those are very, very strong bonds, very, very high melting points, stuff like that. Sodium chloride would be an example of that. You have a positive sodium and a negative chloride, but you could also have polyatomic ions. So it could be, for example, ammonium nitrate, which is an NH4 plus cation with an NO3 minus anion. So there's all different possibilities, and ionic bonds are something we'll talk about this quarter as well. Covalent bonds are when nonmetals usually come together with nonmetals, and the electrons in those examples are shared between the atoms. And mostly, a covalent bonds is between nonmetals and nonmetals. There are some exceptions, but that's kind of beyond this course. Now, ionic and covalent are both really important. All right, ionic is stronger, covalent is weaker, and you might think, oh, covalent bonds are lame. But in reality, life needs covalent bonds. It needs bonds that are flexible, that forms readily and stuff. So without covalent bonds, we wouldn't be here. So covalent bonds, woohoo, kind of cool. Now, in reality, most bonds are somewhere between ionic and covalent, all right? But in general and stuff, we can think about them as one or the other. Now, in addition to ionic and covalent, there is also a type of bonding which we haven't talked about yet called metallic. It's only for pure metals. We'll talk about metallic bonding more in a future section. And also, as of December 2018, there's an idea floating around that there's something called metavalent bonding. And metavalent bonding is mostly for metalloids. So it's kind of like I think of it as the halfway point between ionic and covalent bonds. Metavalent bonding is still very new, so there's going to be more stuff coming out about it, I'm sure. Again, most of the time in this class, we're going to focus on ionic and covalent. I will mention metallic a little bit, but realize past these courses, you might be seeing some metavalent bonding as well. As an overview of the three kinds, all right, we've got the first column, which is covalent bonding, the second column, which is ionic bonding, and the third column is the newest metallic bonding. And most of the time, we're going to talk about covalent bonding and ionic bonding. So let's talk about those, especially in more detail. Covalent bonding, mostly for nonmetals, sometimes metalloids. Electrons are shared, all right? Pretty cool. Now, in an ionic bond, you always have a metal and a nonmetal, or a cation cation and an anion. Electron transference is 100%, and in covalent bonds, you have just electrons shared. So in ionic, the electrons are actually being given up by the metal to the nonmetal. In covalent bonds, the electrons stay on the atom, but they're shared amongst other atoms. If you're curious about metallic bonding, it's only for metals, all right, metals or their alloys. Coulomb's law is what we used in Chem 221 to talk about the strength of ionic bonds, and we're going to revisit that a little bit. Now, in this equation, all right, this is the full version of Coulomb's law, and in physics, you can use this to calculate the force, the newtons between different objects and stuff, and that's totally cool. What we're going to do in chemistry is talk about the results of Coulomb's law, and I'd like you to focus on the top part, which shows the charges. So N plus E says the number essentially of positive charges, and N minus E is essentially the number of negative charges. Focus on that, and also focus on how in the bottom there is the distance between atoms. So what that means, if the distance is too big, you won't have any force between the ions. On the other hand, there's going to be some ideal distance where it works out well. So we're going to use the distance and the number of charges to kind of understand ionic bonds. This is a picture I believe I showed in Chem 221. The middle part there is the lithium fluoride molecule. And lithium is a positive 1, so N plus is just 1. And fluoride is negative 1, so N minus is negative 1. And you can see there the distance D is literally the distance between essentially the centers of the cation and anion system. Now, the first little square brackets right here shows positive 1, negative 1 versus positive 2, negative 2, and realize that those charges in Coulomb's law are being multiplied by each other. So 1 times 1, and you can ignore the signs for right now, 1 times 1 is just 1. So the force between a positive 1, negative 1 is strong, but it's nowhere near as strong as a positive 2 times negative 2, because like 2 times 2 is 4. You get a lot more force, i.e. attraction, between a positive 2, negative 2 than you do a positive 1, negative 1. And I use the idea sometimes how a positive 1, negative 1 is like a single handshake. Hey, how you doing? Nice to see you. Okay, good. That's really cool. But if someone said, oh, I don't want you shaking hands, they could break it up pretty easy. On the other hand, a positive 2, negative 2 is like when you go up to someone you haven't seen for a long time, you're like, oh my gosh, I haven't seen you forever. And you grab on with both hands and you hold really tight. You're so excited to see him. All right, well, a positive 2, negative 2 is kind of like that. And it takes a lot more energy to break that up than it does just a single handshake, positive 1, negative 1. The last little square brackets on the right is the effect of distance, all right? And as the distance is pretty small, you're going to have more force. On the other hand, if the distance is large, you won't have as much force. So let's say I'm coming up to you and I'm like, hey, how you doing? And I shake your hand, all right? There's going to be some ideal distance between you and me where we can have a cool handshake. But on the other hand, if, I don't know, you're nervous about shaking my hand and stuff, which is fine, so you kind of start backing away. Well, at first we can kind of shake hands and then maybe just the pinkies will hold on, but finally there's going to be a distance where there's no more handshaking. It's too far away. Our hands don't extend that far. So as the distance goes up, the amount of handshaking force goes down. That's kind of the idea here with ions, all right? If they're close, all right, there'll be a strong force and they're very highly attracted. On the other hand, if the distance between them is large, then it's going to be harder to shake hands and you won't have a very good force. Now, we can use the positive 1, negative 1s right from the charges of the cations and anions. That's no problem. The distance now, we can begin to do a little bit more than we could in Chem 221 because we saw the periodic trend for size generally gets bigger as you go left and down. So we can make ideas as to biggest atoms, smallest atoms, and again, as the atoms are smaller, they'll be tighter because the distance between their centers will be smaller. If you have a big set of atoms, then the distance will be larger. You won't have as strong of a force.
Atoms have 3 distinct electrostatic interactions with each other. The electrons repel. Similarly, the nuclei repel each other. Finally, the electrons on each atom are attracted to the nucleus of the other atom. When this attractive force is greater than the combined repulsive forces, a chemical bond forms.
It's amazing that bonds form at all, because if you think about what we know so far about charges, positive and positive repels, negative repels. So the electrons of two atoms will repel and the nuclei of two atoms will repel. It's only the attractive force of the electrons from the first atom to the nucleus of the second atom, as well as the electrons from the second atom to the nucleus of the first atom. Those are the only things that make atoms come together. And sometimes you just can't make a bond between two atoms, and that's because the repulsive forces don't allow it. All right, they're greater than any attractive forces you might have. So think about this in the back of your mind, like some types of bonds just don't happen. The repulsive forces are certainly greater in those cases than the attractive forces. So covalent bonding is going to be the focus of the first two chapters, definitely this one and the next one, arguably even the third chapter too, but that's kind of a special thing. We're going to revisit ionic bonding and metallic bonding in future chapters after these first couple chapters. What is important right now is to know if a compound is ionic, covalent, and metallic, and that's not difficult to know. Ionic means it has a positive and a negative, and that usually means a metal and a nonmetal. Covalent is almost always just nonmetals with nonmetals, and metallic is just going to be pure metals or one of the alloys. And remember, the metalloid line on the periodic table is what separates the metals on the left from the nonmetals upper right, so you can kind of make a guess then what's happening.